So we have talked about global monsoon as a concept before, and in this context of interseasonal variability, I just wanted to include a podcast on this new paper from Bin Wang and his colleagues. As you know, Bin Wang is the biggest proponent of this concept of global monsoon. Basically, they look at the annual rainfall, and if that's greater than 60% in the summer season in either hemisphere in any given region, they brand it as monsoon, and then that becomes global monsoon because you consider it together. And of course, that's also mechanistically possible to relate them, because as the ITCZ moves, there are monsoon regimes created in both hemispheres in their respective summers. So you start with this kind of climatology of global monsoon. We have looked at the mean elsewhere. This is a climatological intraseasonal variability activity in monsoon seasons, and we are only looking at land, so you have to be always careful about that as well. And this is averaged over 1979 to 2018. Looking at ISV intensity in millimeters per day, usually they tend to combine the summers in each hemisphere. So this is summer, so May, June, July, August, September for the northern hemisphere, and November, December, January, February, March for the southern hemisphere. So you are plotting different seasons together, different halves of the year. This also means that you are overlapping the Madden-Julian oscillation season into this, where you know that Madden-Julian oscillation is very strong during October to April, and many times we call also boreal summer interseasonal oscillation, which includes the northward propagating monsoon interseasonal oscillation, and how monsoon or the summer rainfall is affected by the MJOs becomes important as well, because MJOs have a certain time scale, something like 20 to 60 days or 30 to 60 days depending on who you are talking to, and so on. Keeping all that in mind, we are looking here at the global land monsoon regions as outlined by these red lines here: North American, South American, North African, South African, South Asian, East Asian, and Australian monsoons. Okay, so those are the major regions, and these are plotted as standard deviation of the 8 to 70 day bandpass filtered precipitation anomalies. Then we will split this 8 to 70 into high frequency going from 8 to 20 and low frequency going from 20 to 70, which have different mechanistic processes involved and different contributions of MJOs, for example, and their prediction skills, predictability are also different. Okay, the global red lines, the East Asian, South Asian regions are separated by this gray line here, which is a little arbitrary because some of the other studies show that this transition is not so abrupt over here. Obviously, moisture is coming from across here, and systems are propagating from here into this domain, and so on, as we will see in a minute. A monsoon region is defined as the region where the local summer minus winter precipitation exceeds 300 millimeters and the summer precipitation exceeds 55% of the annual total. So there is a threshold in the total rainfall and a threshold in the seasonal summer contribution. B shows 8 to 70 day ISV variance contribution to the daily precipitation variance. So where is it that the ISVs are very strong and contribute to seasonal amounts, and where it is that they are weaker? So you can see here the variation of the ISV contribution in percentages. So you can or variance contribution. The contribution is calculated by the ratio of the averaged power spectrum in the intraseasonal band to the total power, and the area conserving format is used. So there are some statistical details which you may want to pay attention to if you are very keenly interested in this. But you already know that there are some regions where the ISV intensity is strong. For example, compared to the North American monsoon, it's much stronger here. not so strong in the North and South African monsoons, but very strong in parts of the South Asian and East Asian monsoons, as well as the northern edges of the Australian monsoon. This itself is a monsoon as well over the maritime continent, but we don't bother with it here. There are reversals of circulations and seasonalities of rainfall. Looking at the average intraseasonal variability intensity measured by standard deviation of 8 to 70 day bandpass filtered precipitation anomalies, which is shown here, you can look at the intensity for each monsoon region and contribution to the daily variance, total daily variance. I won't dwell on it too much, except to say that almost all of them have a strong intensity. South Asian monsoon is strong here, and so is the Australian monsoon, and the rest of them fall here below 5 millimeters per day. And contribution to of the ISV to the total daily variance is also over 30% here and here, but the rest of them are under 30%. So these have implications in terms of mechanisms, their proximity to the equator, their contributions from the contributions they have from MJOs, and so on and so forth. So this is, oops, I don't know why I put that in again here. I might have, yeah. Okay, so this is the power spectra of the ISVs of individual summer monsoons. Power spectra of the 3-day running mean precipitation anomalies in millimeters per day averaged over each monsoon region for the northern hemisphere and southern hemisphere during the summer of 1979 to 2018. Daily climatology is removed to obtain the anomalies. Each monsoon precipitation series is normalized before the spectrum analysis. Dashed lines denote the corresponding 95% confidence limits here. So in the northern hemisphere and southern hemisphere, obviously you have South Asian, East Asian, North American and North African monsoons, and you can see the peaks above the 95% confidence levels crosses the low frequency band here only for the South Asian monsoon, and in the high frequency band 8 to 20 days almost all of them are above the confidence limit in terms of the power in the spectral analysis. In the southern hemisphere, on the other hand, Australian monsoon has a significant low frequency and high frequency peak, but the South African and South American monsoons have a small peak in the low frequency and peaks in the high frequency. So all of them are combinations of high frequency and low frequency, which matters because the usable information in both bands, if they can be predicted, maybe they have different applications in agriculture, for example, or for water management, water resource management, health, and so on and so forth, energy maybe. Okay, fractional variance of the 8 to 20 day and 20 to 70 day ISVs. So now we are going into high frequency and low frequency ISVs against the total 8 to 70 day ISV for average summer monsoon precipitation over each monsoon region. Again, you can see that high frequency has significant contributions in the well, all of them are higher than the low frequency ISV, but East Asian monsoon has almost 70%, North American 68, all these and North African. So these are dominated by high frequencies as opposed to the others, which are somewhat relatively lower. Even South African monsoon here has high frequency ISV variation, okay, contribution to the 8 to 70 day. 20 to 70 day correspondingly lower. So in the South Asian they are almost, pretty close to each other, as opposed to here where they are far apart. Similarly here, here, and here. Okay, so you can see that if you have a similar, almost similar contributions from high and low frequencies, and only low frequencies predictable with some skill, then obviously that means you are missing large fraction of the high frequency ISV that is not predictable or not predicted well as of now. Dominant ISV modes in individual summer monsoon regions, the spatial patterns of the first EOF mode, empirical orthogonal function modes of summer subseasonal precipitation anomalies in millimeters per day. This is for the 8 to 20 day ISVs, and this is for the 20 to 70 day ISVs, and basically confirm what we just said, that high frequencies are there in every region, but in some regions they are much higher than in other regions. Okay, so this is the EOF, so you have to be careful about the time series that goes with them as well. So the spatial loading is to be considered together with the time series, and the negative sign here doesn't have direct meaning in that sense, because the time series could be negative there, while the spatial loading is also negative in case you have positive when you multiply them together, right? Similarly, in the 20 to 70 day band, you have low frequency contributions here and very strong here, here, and here, and not so strong in the other regions. And the high frequency is not so strong here, not so strong in these regions, for example, compared to the total. Okay. In terms of mechanisms, they look at each region and they create a lead lag map of the circulation anomalies. So for South Asian, East Asian, North American, and North African, for example, in the Northern Hemisphere, they go from day -8. I hope this is not pentads. Yeah. So let's read the caption first. Origins and propagations of 8 to 20 day, it cannot be pentads because it's 8 to 20 days. ISVs in the Northern Hemisphere monsoon regions. Shown are the lead lag regression maps of the 8 to 20 day bandpass filtered OLR anomalies, outgoing long wave radiation anomalies, which correspond to the convection and deep clouds in watts per meter squared, and wind anomalies vectors in meters per second, on to the PC1 during summer of 1979 to 2018, and basically, and this is for East Asian, South Asian, East Asian, North American, North African monsoons. Okay, basically you're trying to see if there are propagating features. So if you start in day -8, okay, so maybe I should be more careful. A, B, C are at 850 hectopascal, whereas in D they're at 200 hectopascal. Why do we do this? It turns out that there are often intrusions of mid-latitude waves which typically arrive at the upper levels, 200 hectopascal, and sometimes they force lower level circulation. For example, if there is a strong divergence in the upper level, it can force a convergence in the lower level and vice versa. So you always have to be careful to see where the processes are controlled by heating and waves within the tropics, and where the mid-latitude contribution is significant. So you can see that here the anticyclones, letter A tracks the anomalous anticyclone associated with the monsoon intraseasonal variations, C the cyclone, S the southerly, N the northerly, easterly, and westerly anomalies. So you have anticyclone that is spread out here, goes into the domain by day -6, day -4 it's got now an cyclone anticyclone pair, and the anticyclone is now again organized differently here. And in the paper they basically give you very brief descriptions on how these processes are related to either MJO forcing. I will read the summary in a minute. So MJO is typically got Kelvin waves and Rossby waves and Rossby gravity waves, and every time you have a heat source, obviously you are generating waves. And you remember from the MJO mechanism discussion that we always have waves, convergence, moisture loading, and vorticity, and so on and so forth. So multiple theories, each one emphasizes a slightly different process, but as I said before, when you have multiple theories, that means we don't have a consensus or a complete understanding. So here it's generally good to look at which waves are contributing, whether they are tropical mechanisms that are contributing or mid-latitude waves that are contributing. So without going into those kinds of details, you can see there is more of an east-west mode, and systems propagating from the northwestern Pacific into the monsoon domain here, for example. And here you have much more of a north-south pattern with much more contribution from mid-latitude waves. North American monsoon is got mostly northerly and southerly winds, and then anticyclones showing up here as well. In the North African monsoon, you have westerly winds and easterly winds, and we don't invoke cyclones and anticyclones or wave propagations so much here. So I'm being very brief, but the paper is also just a very brief review, and the contributions of various waves and MJO modulation of the low frequency. So MJO, its time scale projects onto the low frequency part, or the 20 to 70 day part of the land monsoon that we are looking at. This is similarly for the southern hemisphere summer monsoons, looking at Australian, South American and South African monsoons, and now you can see cyclone and propagation features happening here. The red line here denotes the trough center at 850 hectopascal. Just to add, MJOs propagate from the Indian Ocean over the maritime continent into the Western Pacific, and of course sometimes across back to the Indian Ocean, but sometimes they're detoured and go over the gap between Indonesia and Australia. So you expect that Australian monsoon is going to have much more contribution from MJOs, especially in its low frequency intraseasonal variability, and that turns out to be the case. So without going into further details of these various contributions, let's just look at a schematic of how MJO modulates the 20 to 70 day ISVs in individual summer monsoon regions. So this is the boreal summer, so summer land monsoon in the northern hemisphere, austral summer, so southern hemisphere land monsoon. Red arrows indicate lead correlations between MJO convective center in the equatorial central Indian Ocean or negative convective anomaly in the tropical western Pacific. So you have convergence, rising motion here, and descent and sinking motion here. And the leading modes of the 20 to 70 day ISVs over individual monsoon regions during boreal summer and austral summer. Shading over the ocean denotes regressed OLR anomalies in watts per meter squared onto negative RMM2. So we are jumping around a little bit here. As you know, MJO is defined by these real-time multimode index, multivariate index, RMM1 and RMM2, which is a combination of OLR and the shear in the vertical from 850 to 200 or so. And there are many details. For example, when we predict MJOs, we typically predict RMM, and that doesn't always translate to prediction of rainfall, for example. Okay, so those things have to be kept in mind. Shading, so that's OLR anomalies. The shading over land depicts leading EOF pattern in millimeter per day of each monsoon. The sign of the EOF in 3B is reversed when maximum correlation coefficient is negative, just to make them look similar. The values in red indicate the maximum correlation coefficient, and the values in the bracket show leading days. All correlations are significant, of course, which has to be tested always. So you are seeing MJO influence at 12 days lead, 22 days lead here, 15 days, 17 days, and so on. So you can see basically the idea that MJOs modulate the low frequency 20 to 70 day intraseasonal variability in the land monsoon in both hemispheres, and the correlations are significant, but you can see that they can be small, 0.17 here, for example, 0.16, 0.15, here it's higher at 0.30, higher at 0.26, and so on. So what do you do with it? Basically, mechanistically speaking, we don't know if MJOs are completely independent of the ISVs in the land monsoon, but when you use the constructs like RMM1 and RMM2 to define the MJO and do the monsoon ISVs with bandpass filtering, obviously you will end up with two processes, and then you say MJO is in the lower frequency and it modulates the intraseasonal variability in the land monsoons, global land monsoons. Okay. Trends in the ISV intensities of individual summer monsoons during 1979 to 2018 is an older paper led by Binwang Binwang as well, which has argued that the northern monsoons have intensified over these similar periods, and there is some contribution from greenhouse gas increases and some from aerosols and so on and so forth. And here the idea is that the high frequency intraseasonal variabilities have increased, especially you can see here, and correspondingly the low frequency intraseasonal variabilities in global land monsoon have decreased in recent periods. Why does it matter? Because when you look at the subseasonal skills in each monsoon region for the northern and southern hemisphere, the higher frequencies drop off. I have to be careful here again. So the correlations between observed precipitation anomalies in the CPC data and multimodal ensemble mean of 11 subseasonal to seasonal prediction models hindcasts averaged over wet regions of the leading ISV modes that we have been looking at. For the northern hemisphere and the southern hemisphere monsoons, correlations are calculated from leading 2 to 30 days for the hindcasts initialized around the 1st, 10th and 20th of each month during the monsoon summers of 1999 to 2010. Shading indicates one standard deviation among 11 S2S models, and dotted lines indicate correlation coefficient significant at 95%. So when you drop below this, your skill has dropped below 90% confidence limit compared to observations. C shows a correlation of weekly precipitation anomalies averaged from week 2 to 4 for multi-model ensembles and each model symbol. So these are the models that are used. Okay, so the main message here is that the high frequency modes have lower prediction skills than the low frequency ISVs in land monsoons. Okay, so this has to be kept in mind, and the mechanisms for or predictabilities of the low and high frequencies have to be understood, and obviously they keep trying to improve forecasts. And also, because high frequency ISVs are increasing, we have to make sure that the prediction skills don't drop off completely. To summarize the Asian monsoons, high frequency ISVs are primarily related to the westward propagating quasi-biweekly oscillation disturbances that originate from the western equatorial Pacific, and the East Asian monsoon is additionally affected by the southeastward propagating mid-latitude wave trains, which is what we looked at here, for example. Okay. The North American and North African monsoons high frequency ISVs find their preceding signals from convectively coupled mixed Rossby gravity waves and equatorial Kelvin waves respectively. In contrast, all three southern hemisphere monsoons are initiated by mid-latitude wave trains. The MJO directly affects the 20 to 70 day LF low frequency ISVs of the AU monsoon during its eastward journey in boreal winter and Asian summer monsoon by northward and northeastward propagations. On the other hand, the MJO influences American and African monsoons primarily through its associated Kelvin wave component. This will tell you where the MJO phase is when it's affecting the monsoons. Kelvin waves go eastward, Rossby waves go in many directions. Besides, the MJO has substantial impact on South American monsoon through its mid-latitude teleconnection in the southern hemisphere. These divergent origins and propagations of different monsoon ISVs are primarily determined by their geographic locations and associated background calculations. So one of the complex teleconnections you can see here. Okay, so the South American monsoon is affected by the MJO through this complicated connection that is mentioned here. Finally, schematic diagram of propagation routes for dominant ISV modes of individual summer monsoons. Thin arrows show the propagation routes before the wet peak phases of leading ISV modes, same as the shading we saw before in each monsoon region. The purple and red arrows illustrate the preceding quasi-biweekly oscillation in A and MJO in B, respectively. The eastward and westward blue arrows indicate the preceding equatorial Kelvin and mixed Rossby gravity waves, respectively. The yellow arrows indicate the mid-latitude intraseasonal Rossby waves. The broad light blue arrows in A denote background westerly zones where the mid-latitude wave trains prevail. We have learned in tropical dynamics how Rossby waves and background winds interact and why westerly zones are important in that sense. So without going into too much details, you can see there are Kelvin waves, mixed Rossby gravity waves, and Rossby waves and mid-latitudes forcing. Sometimes MJOs interact through the mid-latitudes, as we saw before for the South American monsoon. Okay, all kinds of complicated arrows, but this framework itself, that there are land monsoons, they have interseasonal variabilities, they have high frequencies and low frequencies, and then there is MJO, which is somehow impacting these and almost made to appear independent of the land monsoons, is something you will have to work out for yourself. Okay, so I wanted to include it. It's a bit long, but it doesn't matter because I wanted to finish it in one podcast. The paper is fairly short, fairly easy to read, and has lots of good references, so please follow up if this topic is of greater interest to you. This podcast is just meant as a brief introduction. Okay.